Good afternoon. My name is Brad Huddleston. In this video, I will show you how to use LAMMPS to run a molecular dynamics simulation. First, we'll need to install LAMMPS. Here on the ICME website, icme.hpc.msstate.edu, you can find a link to it. So over here under Material Models and under Nanoscale, you'll find a page that is dedicated to nanoscale simulation tools. And if you scroll down, you'll see that LAMMPS is very prominent because it is one of the main ones that we use at the nanoscale. If you keep scrolling down under Molecular Dynamics Codes, you'll see a link to the LAMMPS code page. And you'll see a link to the repository, which is distributed by Sandia National Labs. Here, you'll see links to several different options for downloading LAMMPS. You can download the source and compile it yourself, which is actually fairly straightforward. You can download Linux executables for Ubuntu or some of the other major Linux distributions, or you can download a Windows installer package, which, as I'm on Windows, that's what I'll choose. And so it'll bring you to the link for the Windows installer package, and I downloaded this 64-bit version. And you can see I already have it downloaded. So once you have the installer downloaded, you can browse to your downloads folder or wherever you installed it or wherever you downloaded it and run that installer. It will ask you for an installation folder where you want to install it. You can use the default one or change it, it doesn't matter. And once you click install, it'll extract everything to that folder and install it. It's very straightforward, so I'm not going to walk through all the details of that. But once you get that installed, you're ready to move on. So next, you'll actually need an input deck for LAMMPS. So if you go back to the ICME website, back to the nanoscale page, and scroll up, underneath LAMMPS tutorials, you'll see a link here. And we're going to follow this one for uniaxial compression in aluminum. We're going to make some changes to it. We're going to change it to copper and a few other things, but this will give us a good starting point. So here's this text of the input script, and you can see more information about this specific script here. But what we're going to do is just copy that and paste it into a blank text file and save it. And I'm going to call it compression2.in. Okay, so just a few words on the basic structure of a LAMMPS input script. There are a few things that will always exist in it. You'll always have some kind of initialization. You'll always have some kind of atom definition where you're defining the atoms, and you'll always have some part where you're defining what the potentials are that will define the forces between the atoms. You may have additional computations that you're telling it to do, and then you'll actually get into what your simulation is all about. And I'll go into more detail about these LAMMPS input files in the next video. For now, we just want to modify this a few things to make it run copper and to make it run a little bit faster for us. So first, we're going to change this lattice parameter to the lattice parameter for copper, which is 3.61. Then we're going to change the pair potentials to use a mean potential. And we're going to change it here, we're going to change this to use library.mean and use the copper potential from that. And then the copper.mean parameter file and use copper for that as well. And those we're going to leave the same. One other thing we want to change here is we're going to change the time step to 0.005 or 5 femtoseconds. And so we're also going to change the thermo to update sooner, and we're going to change the run to be fewer steps there. And then in the deformation section, we're going to similarly change the thermo down to 100, change the run to 4,000, and two other changes related to the output files. We want to change this. This says aluminum. We're going to change that to copper. And then we want to change these two dump lines. So this is actually where it is dumping out the results, the positions of the atoms and other things related to the atoms. And this is what we'll use to look at it in Oviedo later. So we want to change this into a format that we can use easily in Oviedo. So what you can do is just delete that line and change this CFG to custom. And then this right here is the name, and we're going to change that to a different name because this is a different. So we're going to just change that to something like that. And this star means that it will output a different file for each time step. And this will be good. Oviedo will be able to use that as well. Finally, we're going to delete those two entries, those options, and change it just to ID. Okay. And I believe that is all we need to do. So now you can run it. And again, I'll go into more of the details of what I just did there in the next video when we go more thoroughly through a LAMMPS input script and what it is doing. For now, open up a command prompt and browse over to the folder that you have saved your input script in. For me, it is here. And you can see there's a lot of output files, but also this cu.compression2.in, which is our input script. So if you've installed LAMMPS, your executable should be this one right here, lamp serial lmp serial.exe. It also comes with a parallelized version, and if you have a installation of MPI-CH2, you can use that one. However, for this simulation, you shouldn't need it because we're only doing 4,000 atoms, and that can run very easily on a single processor. So you specify the input file by -in and then the name of your input file, and press enter, and it starts running. Now this could actually take about 5 minutes to run, so I'm not going to sit here and watch it, but I do want to show you what you do once you get the output. And we're back. So as you can see, the simulation is finished, and so now we'll actually go and look and see what the results look like, see what the output is. So we're actually going to use Oviedo. So if you go back to the ICME website, back to the nanoscale page again, and scroll down to the visualization section, you'll see lots of different options of what you can use to visualize your atomistic results, your molecular dynamic results. What we're going to do is we're going to use Oviedo, and I highly recommend it. Oviedo is very easy to use and very powerful. It has a lot of analysis tools built in. Easy to download and install. You can get a Linux, Windows, or even Mac version, so you can install one of those. And then you can open it. And we're going to make this full screen here. Once you have Oviedo opened, you can load file. And so you see here's all the files that our simulation created, all these cu.comp numbers. So we're just going to load the first one because that's going to be the first time step. And we're going to want to do one thing so that we can see this more easily. We're going to add modification, and we're going to add a color coding. And we're going to set this color coding to color based on the centrosymmetry. And then we'll adjust this range to go from 0 to, say, 5. And as you can see, there's a variation of colors here. Basically, what the centrosymmetry does is it indicates how close to a perfect lattice structure each atom is in. So these dark purple ones have a centrosymmetry very near 0, and that essentially means that it's nearly in a perfect crystal structure. So all the atoms around it are in the right places. These ones with lighter colors have a relatively high centrosymmetry, which means they're kind of vibrating or something out of their perfect crystal structure. And their vibrations is why you see this variation in colors even before we've started deforming it. The thermal vibrations can get them out of that exact perfect crystal structure. And then as we run this, you can click the play button down here. You'll see it compress, and you can see, that was pretty fast, but you can see here you start getting some very high center symmetry values here. And actually this indicates a dislocation. I mean, you can see they happen in these very specific planes, and so those are dislocations forming. And then you can see it just gets squashed, and then comes back a little bit. But so with that, you've actually done your first molecular dynamics simulation in LAMMPS. See you next time.